Wow. I'm Mike Ravine. I'm from Malin Space Science Systems. I'm here on behalf of Mark Robinson, who's at Arizona State University, who is PI of the ShadowCam instrument. ShadowCam was just selected by NASA as a NASA contribution to the upcoming Korean Lunar Orbiter mission. And this was Mark's title, Seeing in the Dark, which I don't really like very much because it's imaging in the permanently shadowed regions. And the permanently shadowed regions actually aren't in the dark. If you were standing in them, you'd be able to see perfectly well. But he liked the way it sounded. So a little bit of background about the Korean mission. It's called the Korean Pathfinder Lunar Orbiter. It's being run by the Korean Aerospace Research Institute. It's the first of a series of missions the Koreans are planning, which they call their Korean Lunar Exploration Program. It'll be in a polar orbit with a nominal height of altitude of 100 kilometers. It's a 550 kilogram vehicle. The launch vehicle is still to be determined, but the launch is planned for the end of 2020, which means time's a-wasting, and we're going to be starting to build stuff fairly soon. As I said, the NASA participation principally is providing this instrument ShadowCam. There will also be some NASA participating scientist program that will be run at some time in the future using the data from the other instruments on the payload. The mission objectives are principally to develop lunar exploration technologies on the part of the Koreans. They have science investigations associated with topography and environment and resources, which is really the ShadowCam focus. They also have a new technology demonstration. They have a payload element that's a disruption-tolerant network experiment. So the science objectives for ShadowCam, 1, 2, 3, 4, 5. Principally to map the albedo patterns in the permanently shadowed regions and interpret what those are telling us about what's going on in the permanently shadowed regions. To investigate anomalous radar signatures that we've seen on LRO and in the permanently shadowed regions and try to figure out what's causing those. To provide hazard and trafficability information within the PSRs for presumptive future landed missions that would operate there. Associated with that, to map the morphology of the PSRs, to search for and characterize landforms that may be indicative of permafrost-like processes if it turns out the volatiles aren't merely on the surface but are actually buried, which is a real possibility. And then document and interpret any time-varying changes we see to the albedo units, if there are any such, by doing repeated observations. So this is all in the form of, as NASA calls them, their strategic knowledge gaps, the things we want to learn about the moon that we don't know yet, which are mostly associated with finding out where the polar volatiles are, how they're moving, and what you'd need to know if you wanted to be on the surface and actually potentially exploit those. So what we have here is a LROC NAC picture of a crater that's got a permanently shadowed region in it. This is the shadow at the time the image was taken. The red line is actually showing the boundaries of what is the permanently shadowed area inferred from LOLA topography, so the sun's coming from this direction. By operating the LROC NAC in a grossly resolution degraded mode, basically by taking exposures that are 40 times longer than we should take them, and so the pixels are 40 times bigger in the downtrack direction, we can actually get decent signal in these permanently shadowed regions. So this is representative of what we're going to do with ShadowCam, but the resolution is more than an order of magnitude degraded, which is the main reason for flying ShadowCam. But you get a sense that, yes, you can see in these areas, you can resolve features. So this gives you a sense of what it's looked like, except we'll do a lot better from a resolution standpoint. Because this is being done in a cost-constrained environment, schedule-constrained environment, our intention here was to start with the NAC and make as few changes as possible to it to be able to meet the ShadowCam requirements, which basically means we're going to use the same telescope, a 700 millimeter, not centimeter, f3.6 2.8 degree field of view Ritchie-Creation telescope, which, you know, as has been discussed at some length, takes awesome pictures. That's where Neil Armstrong walked on the moon. That's all great and everything. But we can use the same telescope, and we're actually going to start building that telescope in the next couple of months because we have to be able to meet the schedule. So the only changes that we're going to make for ShadowCam is to use a different detector because we need about 2 orders of magnitude increased sensitivity to get good signal to noise in these PSRs. We're going to do that by using a detector that has a somewhat larger pixel size and uses time delay integration to increase the effective dwell time by a factor of an order of magnitude-ish. One interesting thing to note is that means we're building a telescope, we're building a camera, and we're going to send it to the moon. It will take pictures in the permanently shadowed regions, but it can't take pictures outside the permanently shadowed regions because it'll be completely saturated, which is annoying at some level, but that's not what the job was, and it's not like we don't have other cameras there that can take pictures in the illuminated areas. So with the detector that we've baselined, ShadowCam will have a pixel scale of 1.7 meters from 100 kilometers, and we should be able to get, for typical permanently shadowed regions, signal to noise of greater than 100 to 1. So the main reason we're flying this is because there's a whole lot of data about volatile distribution in the permanently shadowed regions from LRO, and it is unfortunately, or interestingly, depending on how you like to look at these things, all indicative but potentially mutually contradictory, which means we need to go take a look at this. We have evidence for water frost from UV observations. We have evidence in the UV that could be water frost or could be high porosity. From the laser altimeter operating in passive mode, we have a near IR albedo, which could be water frost or could be space weathering. The locations where that is seen, the temperatures there, as inferred in the thermal IR instruments, measurements from the Diviner instrument, are consistent with water being stable long-term, ice being stable long-term on the surface. Then we have the neutron measurements for looking at hydrogen from the LEND instrument, which show high hydrogen and presumably water in regions where ice is not thermally stable, which is sort of at variance with everything I just said up till now. There's the mini RF observations that show some craters have very high returns, which could be ice or could be high populations of surface blocks. And then we have images like the ones I showed, the degraded resolution images with the NAC, which we have not found any particular signatures of any anomalously high albedos that one might expect if there was surface frost or ice. So obviously, if we're going to send missions to the moon to try to better characterize and potentially exploit these resources, we need to resolve this because clearly we don't understand what's going on right now. And so that's really what ShadowCam is for. And just to give you some sense, I'm not going to go through this because this is actually sort of recapitulates what I just said. The main thing, this is a model that Dave Page did based on Diviner data, and the main thing to understand here, this is the South Pole, that's Shackleton, and 3 craters that all are off the pole that are also permanently shadowed. The colors here are showing, based on temperature as inferred from Diviner, at what depth ice would be stable on the lunar surface in the long term. So the permanently shadowed regions in all of these craters, any place shows white, ice should last indefinitely on the surface. Away from those, ice is predicted to last indefinitely with some overcovering of regolith. So this pattern is more or less what you would expect, but it also shows that there are places away from the permanently shadowed regions that potentially are also places where there could be ice. So, from an could you push the little button there? So this is actually not real images, but simulation. That's Shackleton there, so the South Pole is right there. And this will give you some sense of what the lighting environment looks like over the course of the lunar year. For imaging any particular pole, we want to image there at the local summer because we get a little bit of light in there, but you can see how much it varies because all the light you're getting in these permanently shadowed regions is light coming reflected off of the crater rims. And so our operations concept, which I'll discuss in just a minute, is basically to map the entirety of the permanently shadowed regions associated with each pole in a relatively limited window of time that can be done in the local summer for each pole. So the way that's going to work Guess I won't go until the movie stops. So the way it's going to work, we've a simple mapping configuration we referred to as collars. There's a circle and an annulus around the pole. It turns out going from the pole out to about 85 degrees latitude in both directions, the field of view of the instrument is such that you can get complete overlapping coverage on successive orbits. Going from 85 out to 80, there's gores between each, which you can see there, between each successive orbit. So in a single month, we can map this inner collar with 100% coverage, but there's still, after the first month, there's still gores in the outer collar, and so we have to make a second pass during the second month where we can get repeat coverage in the inner collar and fill in the gaps in the outer collar. I probably also should have said that all these little polygonal shapes are showing where the actual permanently shadowed regions are. This is for the, I believe this is for the North Pole here. So that means in a 2-month period associated with local summer, we can cover each of the poles, 6 months apart, which will be helpful from an operational standpoint. So, and that's that, you've seen that. So that's basically the story. We're just getting started on this right now. The reason that the PI is not here giving this talk is because the spacecraft PDR is being held in Korea even as we speak. The main takeaways from this are the camera will be used to identify, characterize the surface for possible or hopefully definitely future landed exploitation. We'll be using these to characterize the surface properties. We will also, and I didn't really get into this, we'll also, as can be done based on spacecraft constraints, we'll also be making stereo observations in certain local areas, which we'll be able to use to produce high resolution digital terrain models, certainly better than the current LOLA models. So that's basically the story on that. So are there any questions? Oh wow, I actually hit it.